the next part of our unit discusses a logarithmic function. So 3.1 is all about exponential functions, and then logarithmic functions are their inverse. So we need to talk about, remember what an inverse looks like. It's the reflection across the line y equals x. So this is a nice clear example of exponential growth function of base greater than 1. And then his inverse would be a logarithmic function of base greater than 1. So logarithms are actually pretty difficult to graph, even using a graphing calculator. You're going to want to probably think about his exponential inverse in order to graph it by hand. That's how we're going to handle it. Yes, your graphing calculator can help you once in a while, but even the nice technology doesn't do a great job. So this is logarithmic form. Log of some particular base of x equals y. You're going to see me put parentheses around whatever's in the logarithm quite a bit. And then the equivalent exponential form, and these are transferable, is some base to the y power equals x. So we call that the rewriting formula, writing from exponential to logarithmic form and vice versa. And you probably used a lot of that. So that's the same thing that's on your notes. Here we're going to rewrite into the other form. So what I usually do is, this is logarithmic form, I'm going to write an exponential form. So the first thing I do is identify the base. The base is this 14 right here. So I write the base as an exponential problem now. And then the answer is the new exponent, and it equals x. So once you figure out who base is, then basically the other two numbers just swap. There's a reason why this formula is what it is. We'll talk about that in the future. So here the base is this 17 right here. So the base of my exponential is now a 17. And then I raise it to this second power equals 289. Well, that just makes sense. 17 to the second power is 289. But they're not always numerical, so we have to keep that in mind. So now we're going to go to logarithmic form. So I'm going to write down the abbreviation for logarithm. I have to identify who the base is. So the base of the exponential is also the base of my logarithm. Now, inside of that logarithm, basically these two things just swap. So b is going to be what's inside the logarithm. And then my answer is going to be the other number that's left over, 20. So I find going to logarithm form actually kind of difficult. It kind of hurts my brain, so I like to go back and double check. So my base is a 7 in this problem. I'm going to write down log base 7. And then what's in the logarithm is, what is the answer right now? 1 over 343. And then the original exponent is now the answer to the question. Weird, I know. So basically these two just switch. Again, we're going to be using that property quite a bit, so hopefully that's familiar to you, and we're going to be using it a lot, so look forward to that. Here, if you can kind of memorize some of these properties, your life will be a lot easier. So log of any base applied to a 1, the answer is going to be 0. And the reason for that is because if you rewrite this into exponential formula, anything to the 0 power is a 1. So the logarithm properties and exponent properties kind of go hand in hand. Here, if you have matching bases of the exponential and the base, the answer is just going to be a 1. And that's because of this. B to the y power is going to have to equal b to the y power. So, oh, I skipped a property, sorry. That was this guy down here. B to the first power equals b. So these are explaining why all these properties work. Once we realize what exponentiation means, they'll make a lot more sense, I think. So the common logarithm is log base 10. And when you hit the log key on your calculator, they're referring to the common logarithm. That's a very commonly used one in math. The other one that shows up on your keypad is the natural logarithm, which we'll get to next. So if I were to graph an exponential growth of base 10 and then invert all of his points, I would come up with what's called the common logarithm of base 10 graph. And you'll notice all the things that were true for exponential of base 10, it's all kind of inverted for his inverse. So the domain and range switch, the y-intercept is now the x-intercept. All of this is going to make sense once we get to graphing. And here's our friend the natural logarithm. So he is the inverse of base e to the x power. So again, you'll notice that all of these things that were true for e to the x power are going to be inverted but true for his inverse of natural log. Both of those things can be graphed using your calculator, but your calculator doesn't do a great job, so we have to kind of be careful. The properties that we were talking about here, these are them again. We're going to be using them, so get used to them. We're going to do a no calculator section of our quiz coming up. So here, let's talk about this. the way I think about this question is I say 5 raised to what power is going to give me this answer of 1 over 25? Well, I need it to be negative because I need it to flip the fraction, and I need to change a 5 to a 25. So what if we tried negative 2? 5 to the negative 2 is 1 over 25. These are difficult at first without a calculator, I know. So here, 3 to what power is going to give me a square root of 3? Well, instead of writing it as square root of 3, isn't that the same thing as 3 to the 1/2? So I guess there's no more question anymore, guys. The answer is 1/2. Whoops. You could put an X instead of a question mark if you prefer. All right, here the natural log is the same thing as a log base e. So one of the properties of logarithms and exponentials is that if your bases match, they just cancel out each other, and then the 7 would drop down. So same thing here, the e and the natural log would cancel, and the 5 would drop down. And then here, remember log with nothing written as a base, we assume it's a base 10. So 10 and the common log will cancel, and a 13 just drops down. Those are my favorite log problems. All right, remember guys, no calculator here. So 7 log base 7 of base 7 exponential would cancel, but remember there is an invisible little 1 up here. So while these cancel, you do have a 1 that drops down. This is a common logarithm again. So they cancel, and the 5x drops down. And then 3 to the log base 3 cancels, and the 2 drops down. So those were pretty basic. We didn't have to do any rewriting. Here we have to do a little bit of rewriting. Ready? So if I could rewrite 36 as a 6, life would be good. So instead of 36, let's say that's 6 squared. Now that the bases match, log base 6 of 6 are going to cancel, and the 2 drops down. All right, similarly here, I need to rewrite 81 so that it's a 3. So 3 to the 4th power is 81, but if I want to make it a fraction of 1 over 81, we just have to negate it. And remember, no calculator. So these cancel, and you get a negative 4. And this one's easy peasy, lemon squeezy. E and natural log cancel. It's just x squared. All right. Trying to get this recorded before class starts, so hang tight. Here's some more examples. You do a lot of rewriting. So like here, you would have to rewrite this as, 8 to some power, which without a calculator, you might have to think a little bit, right? Because like 8 squared is 64. I'm guessing it's 8 to the 3rd power, but I don't know. I might give you a chart or something if we test and I give you big numbers like this. 64 times 8. Yeah, sure. All right, so here, log base 4, they'd cancel. I think we decided that was a 3. All right, here, you're going to have to rewrite 1 over 32 as a base 2. So in order to make a 2 a 32, that would be 2 to the 5th power. But in order to flip it to a fraction, you're going to have to make that a negative 5. So the answer is negative 5. This one's actually really tricky. So this is 16. And then we have to change it to a square root of 2, which is 2 to the 1/2. Yuck. Okay. Boy. So, if I wanted to make that a 16, holy cow, this is tough. All right. 16, but written as a 2, that would be like 16 to the 4th root of 16 is 2, so that's a 1/4 power. But remember, he was already raised to the 1/2 power. Ugh, gross. So 1/2 and 1/4 together as powers is 1/8. Oh, gosh. So this is log base 16 of 16 to the 1/8 power. So finally they're going to cancel. And the answer is 1/8. Okay, how would I promise you I will never give you one that nasty on a no calculator test? Oh my goodness, that'd be awful. Alright, so again, more guided practice. These are all common logarithms, so not a lot of fun. Alright, moving along to financial literacy again. Okay. That's what your book calls story problems with money, apparently. We're trying to invest $3,000, and she wants to compound continuously at 6%. And then we have this formula right here to use, which is just a rewrite of a formula that we actually kind of already know, but we'll get into that later. A is the current balance, and then P is the original principal. R is the rate, yada yada, and then I want her balance to come out to 6,000. So that's the A. The original amount was P. There's the R. So going into our formula here, we're going to have natural log of 6,000. Oops, minus natural log of 3,000. You don't need the parentheses on your paper, but when you type in your calculator, you're going to have them. Equals my rate times t, which I still don't know. So once I type this in, then I'm going to have to divide by 0.06, which I'm trying to save a little time here, guys. So if you need to pause and type, go ahead. But when I did that, I ended up with t equals roughly 11.6 years. So she's going to need to leave her money for like 12 years. Good luck, lady. All right. Seismology, the Richter scale, measures the magnitude of an earthquake. So this is the formula. And E is the energy that's released. If the amount of energy released is 1 million kilowatt hours, what's the reading on the Richter scale? All right, so we need to plug in 1 million right there. Okay. And I actually haven't done this one, so I don't have a calculator, and I want to pull up my other one. So you guys would just type 0.67 common log, parenthesis 0.37 times 1 million, close your parenthesis, and then plus 1.46. You should get an answer of like somewhere between, I don't even know, like 4 and 10, because the Richter scale, usually it's like seismology Richter scale answers are like a 7.2 earthquake kind of thing, you know. All right, graph of a logarithmic function. This is not as exciting as it looks. So remember exponential growth and decay graphs. Everything you know about them, we're going to have to reverse it because logarithms are the inverses of all those exponential growth and decay graphs. So once you figure out who the base is of the logarithm that you're trying to graph, then you can interpret what the log looks like because you're going to invert some points. So if you have a base greater than 1, that is the inverse of a growth. Remember, it's the inverse line here of reflection. So here's a growth, there's a reflection line, there's your log. But if you have an inverse of what used to be a decay graph, the logarithm looks different. They do have a lot of things in common, though. Domain is 0 to infinity, range is negative infinity to infinity. So that's the reverse of our exponentials. There's no y-intercept this time, but there's an x-intercept at 1 for the boring functions. The end behavior is going to look totally different. So we got to be real careful about this, okay? It says watch out for transformations. Log of x plus 4, so remember it's x minus h plus k is the transformation formula with an a in front if you want to leave it there. So x plus 4 really means left 4 units. Order still matters on transformation, so watch out. This negative is a reflection across the x-axis that has to happen first, and then it's translated 5 units down. And then here, order doesn't matter in this one so much, however, it is a vertical stretch by a factor of 3, and then this x plus 2 would be a left 2 unit shift. So those transformations that we already know all about, we're going to see them again. Yay. Alright, so here what they did was they graphed an exponential of base 6, so they graphed this guy, and then they took the ordered pairs and they flipped them around, and that gave them the log of base 6. Your calculator doesn't have a log base 6 button. I mean, we can get fancy and use something called change a base, but it's actually easier if you just graph the exponential. Alright, so here, let's see, are we on our notes again? Yeah. So what I'm going to do is, and you can go ahead and get your calculator out and start typing. You won't be able to find log base 3, but if you could type 3 to the x power in your y equals and get some ordered pairs, and then we can reverse them for the logarithm graph, because inverses have reversed ordered pairs. So like negative 2.11 is a estimate for an ordered pair for the 3 to the x power. Negative 1.33 roughly. 0, 1, 1, 3. So what we're going to do here is we're just going to reverse all those points. So 0.11, negative 2, negative 1.33, 1, 0, and 3, 1. And you're going to graph very carefully, of course. I'll do the easy ones. Oh, I think Abruzzo. girl. Alright, so this is 0.33, negative 1. I was like, that's not working. 0.11, negative 2. There we go. So basically you end up with, oh jeez, something that looks like this, and then it comes down along the vertical asymptote this time. And they want us to identify some stuff. So there is a vertical asymptote at the y-axis, which we will call x equals 0. The domain is 0 to infinity. The range is negative infinity to infinity. What else do they want? Intercepts. There's no y-intercept, but the x-intercept, I can see right here, it's at 1, so 1, 0. We already said the asymptote. So end behavior, this is the weird one. I'm going to leave both parts of my end behavior blank for a moment, because it's not as simple as going left and going right forever. Because we don't go forever on the domain. So for my x goes to, usually I'd say negative infinity, it's not going to get to negative infinity, it's going to kind of stop at the asymptote. So as x approaches the asymptote is 0, your function's heading downwards, so to negative infinity. That's confusing, I'm sorry. And then as x goes to, it never stops, so it goes to the right forever. The function is going up forever as well. So very confusing for logarithm end behavior. One part of the end behavior is going to approach the vertical asymptote. So keep that in mind. Alright. I am slightly running out of time here, but the transformations here, we have a reflection over the x-axis and then a right 2 shift. So if you think about all these ordered pairs being reflected over the x-axis and then shifting right 2, a lot of things happen, and the most notable one is that the vertical asymptote is now going to be over here at 2. So this ordered pair of 1, 0 gets reflected, still here, but then it shifts right 2. There we go. And then like this nice ordered pair, which used to be at 3, 1, if it got reflected and then shifted right 2, now it's over here. So after you get a few points, yuck, oh man, you'd be able to kind of fudge in a graph if you weren't drawing on a tablet. And you would find a new graph that has all new features. So domain is now 2 to infinity. And then the range is still negative infinity to infinity. That's not going to change. The vertical asymptote is now at x equals 2. The x-intercept, I think it ended up at 3, 0 now. The end behavior is very strange though. So, again, I'm going to leave all 4 parts blank for a moment, because one of the parts is approaching the asymptote, the x, which is unusual. Alright, so as x goes, it's not going to go forever left, it's going to approach the asymptote at 2. My function's going up. And then as x goes to the right, which it does go forever, to infinity, my function's traveling down. Okay. I think end behavior on logarithm graphs is actually really stinking tough, so I apologize. Alright, investments. This is a good one. They give you a nice formula here to use. And then P is the present value, P sub naught is the initial investment. So here's your initial investment. And they want it to get to 7,500 in 2010. So the amount of years that have gone by, 2005 to 2010 is 5 years. So using our formula, R equals 1 over 5 natural log of, okay, they want my present value first, so 7,500 over 4,000, all inside that natural logarithm, which I would just type on my home screen, and I get roughly 0.13. So it's an investment return of 13% approximately. That is another derivation of the formula that we are going to be using, and once we get more comfortable with solving logarithmic equations, we'll see where all these are coming from. So another financial question, similar formula here. T equals natural log 2 divided by k, where k is now the interest rate, which you usually say R, so don't panic, as a decimal. So $5,000. And they want it to compound continuously at 4.5%, and they want it to double. So the $5,000 is actually not necessary for these doubling problems, and that's why you see a 2 in the formula. It doesn't matter how much money you start